this idea of there's a bunch of information and it maps into something that we might think of as a three-dimensional image. Victoria, can you put Leonard's first slide up? Okay, what is this here?
First one? That's a microscopic picture of the film of a hologram, but it's about what it would look like. It's about what, if you look through the microscope at the film, not this thing that is being described by the hologram, but by the piece of film itself, it would look approximately like that.
And so then if you put light through it in some particular way...
Right, well, let's first. It's got some information in it. It's all scrambled. It's impossibly scrambled. You can't look at this and see what it is.
Let's see.
Well, okay, go to the next one.
Let's go to the next one. Here's the... Stand by, folks.
All right. All right, so if you do the right thing with a hologram, namely shine light on it and so forth, it'll reconstruct an image.
So you got the flashlight. Maybe this is obvious, but the flashlight going through the film, and somehow the information in the film recreates the 3D image of the clown smoking the cigar.
But the interesting thing about it is that the clown is three-dimensional. You can go behind it and you can see whether he has hair on the back of his head. You can go underneath and look at the chin underneath. In fact, if this hologram had been made not with ordinary light, but if it had been made by an NMR scan, you could have coded on that boundary, on that surface, you could have the interior, you could have all your guts and blood and everything else, bones. The entire full three-dimensional structure would have been mapped. You used the word mapped, and it's a good word. Mapped onto the boundary, onto the film. And the important thing is not that you shine light to reconstruct it, but that the information about the clown is equally well and, in fact, in some sense, better described, more accurately described, more precisely described by the little dots and dashes and structures that are entirely scrambled, totally impossible for you to just look at, but it's there. It's there in that film.
It's there. And as you say, you can add detail to that informational film infinitely, or is there an upper limit?
Okay. So in the world that we're talking about, which is the real world, there's a limit. No more than 1 bit, and that means a plus or a minus, one little dot per Planck area. The Planck area is a certain unit of area that's made up out of the fundamental constants of nature. It happens to be about 10 to the minus 33 centimeters on a side. It's far smaller than anything that physics studies experimentally. No more than 1 bit, that means a black dot or a white dot, per Planck area.
All right, so let's just back that up for a second. Just as you need a certain amount of resolution on a piece of standard film or a digital CCD chip to produce an image that's recognizable of your lovely pets or your kids or something like that. In physics, 1 bit of information, is it a traditional bit as though?
Yes, it's a yes or no question.
A yes or no question. So a 0, 1 bit
0, 1.
is necessary to specify a Planck space, which is an infinitesimal but measurable a little chunk of space.
Well, and so what it says, I mean, in essence, what it says is this entire room, everything that's in it, can be in principle described mathematically in terms of degrees of freedom, structures on the boundaries, on the walls of the room, with never needing more than 1 bit of information per Planck area. That was very radical. That was very surprising because people had always associated information with volume. There's the room, if you like, there's the room. And I'm going to describe the room, everything that's in the room, by dividing it up into little tiny cells. A cell, let's say, no bigger than an atom. And what can we ask about a cell? We can ask, is there or isn't there an atom in it? Of course, we can ask what type of atom, but let's ignore that. Is there or isn't there an atom in it? And if we didn't have to worry about the type of atom, that would be a complete description of everything that's in the room. And so there would be one decision for each voxel. A voxel is a word that means a little cube. There would be 1 bit of information per voxel. It's either empty or it's full. What we found, in essence, is that's too much information. No room can ever have as much information as is implicit in this picture here. The amount of information that it takes to describe the room is more like this picture here. 1 bit of information per surface area. So I like to say the world is pixelated, not voxelated. The world is made up, or the degrees of freedom of the world, the most accurate description we can ever have is in terms of a number of degrees of freedom which is proportional to the area and not the volume.
So it's actually the reverse of our intuition,
Very
and
much.
Gerard, help me out here. So we like to think of, gosh, you know, movies are great, but wouldn't it be fabulous to have IMAX 3D? In fact, what physics says is you can get all the information in your 3D high-res reality world on a 2D surface.
Let me just, one thing before I want to get these guys.
Yeah.
The only thing is that the two-dimensional description is going to be monstrously scrambled, very difficult to decode, very difficult to see what it's a picture of. That's the cost of coding information in 2 dimensions instead of 3.
Right. As a mathematician, your first reaction will be there's much less space on a 2-dimensional surface than in a 3-dimensional world. So your first reaction is that can't be right. We will be missing enormous amounts of information if we try to scramble everything on a surface. However, you have to remember that this is the Planck length, which is extremely small for all standards. 10 to the minus 33 centimeters is extremely tiny even in units of elementary particles. So even this looks at first sight to be very little information. Actually, it is enormous. It's gigantic. But on the other hand, you have to realize that not only what's in this room should be mapped on the surface, but the entire universe can be mapped on the surface. That's even more gigantically crazy, because you would think that the surface of the universe would be much smaller than its volume. But again, these Planck units are so small that still you have enough information on the surface to specify everything that goes on in the universe.